welcome to another module in this massive open online course on MMSE or Bayesian MMSE estimation for wireless communications. All right. So, we are looking at the MMSE estimate of the wireless channel coefficient, of the fading channel coefficient H, based on the transmission of n pilot symbols, right. If we denote the pilot vector by x bar, we have derived the expression for the fading channel coefficient, and in the previous module we have shown that the estimate of the fading channel coefficient is h hat equals, this is given as, well, sigma h square times x bar transpose into sigma h square x bar transpose plus sigma square identity times we have y bar minus x bar h plus x bar mu h, x bar times mu h plus mu h. This is the MMSE estimate of the channel coefficient h, correct. This is the MMSE estimate of the channel coefficient, MMSE estimate of your channel coefficient h. Now, what we are going to do is we are going to simplify this expression to obtain an expression which is much more simpler to analyze and basically to derive insights from. Okay. So, we are going to simplify this expression. Now, realize, similar to the wireless sensor network scenario, we can start with sigma h square x bar transpose x bar transpose plus sigma square x bar transpose. Now, I can expand this quantity. Now, this quantity, observe that this quantity I can expand it in two ways. I can either take x bar transpose common on the left, or I can take x bar transpose common on the right. So, if I extract x bar transpose on the left, what I am going to have is this is x bar transpose into sigma h square x bar transpose plus sigma square times identity, and this is if I take x bar transpose common on the right, then what I am going to have is basically I am going to have sigma h square x bar transpose x bar plus sigma square times x bar transpose, and naturally both these quantities are equal, because basically they are simplification of one and the same thing. In one we are taking x bar transpose common on the left, in the other we are taking x bar transpose common on the right. So, these are simplification of the same expression, therefore, these are equal. Okay. So, we can also write this, mention this clearly over here, taking x bar transpose common on the left hand side, taking x bar transpose common on the right, and these two quantities are therefore equal. And therefore, what does this imply? This basically implies, now what I am going to do, multiply both sides by sigma h square. First, multiply LHS and RHS by sigma h square. If we multiply LHS and RHS by sigma h square, we have sigma h square into x bar transpose sigma h square x bar transpose plus sigma square identity. This is equal to, well, sigma h square is a scalar, so it can go anywhere, sigma h square x bar transpose x bar plus sigma square times x bar transpose. Now, what I am going to do is I am going to take the inverse of this quantity, bring this quantity onto the right. I am going to take the inverse of this quantity sigma h square x bar transpose x bar, bring this quantity onto the left over, bring this quantity onto the left over here. So, now this basically we can write this implies sigma h square x bar transpose sigma h square x bar transpose x bar plus sigma h square inverse times sigma h square x bar transpose this is equal to, take this inverse on the right, I have well of course I have to multiply by sigma h square, right. So, this has to be sigma h square, this should be equal to sigma h square x bar transpose times sigma h square x bar transpose plus sigma square times identity inverse. Okay. And now, what we see is this quantity, if you look at this quantity, over here, this quantity, correct, and if you call this quantity as basically let us say this quantity you call it as star, and now you can see this quantity here is basically the same as star, okay, that is sigma h square x bar transpose, correct, sigma h square x bar transpose into sigma h square x bar transpose plus finger smear identity inverse, both these quantities are the same. Therefore, we can write the MMSE estimate h hat can be equivalently written as h hat. Now, before we write the MMSE estimate, now we will do one more simplification. Notice that this quantity sigma h square x bar transpose x bar plus sigma square, this is a scalar quantity. Notice that this is a scalar, correct. In fact, x bar transpose x bar, look at this, this is simply sigma h square x bar transpose x bar plus sigma square, that is equal to sigma h square the row vector x 1 x 2 so on up to x n times the column vector x 1 x 2 so on up to x n plus sigma square. And now, if you look at this, this is basically equal to your sigma h square times x square 1 plus x square 2 plus so on up to x square n plus sigma square and if you look at this, this is nothing but summation x square 1 plus x square 2 plus x square n, this is norm x bar square, correct, this is norm x bar square. So, this quantity is basically your, what we have shown is sigma h square norm x bar square plus sigma square, this is a scalar quantity. And therefore, now if you take a look at this quantity here, I can write this as therefore, sigma h square x bar transpose x bar plus sigma square inverse sigma h square x bar transpose equals, now this quantity is a scalar. So, the inverse is simply going to be its reciprocal. So, this quantity is sigma h square x bar transpose divided by sigma h square norm x bar square plus sigma square. Okay. And therefore, what we are saying is this quantity is equal to your sigma h square x bar transpose plus sigma square identity inverse into sigma h square into x bar transpose. And therefore, the MMSE estimate implies your MMSE estimate therefore, the MMSE estimate we have is h hat equals sigma h square transpose divided by sigma h square norm x bar square plus sigma square times y bar minus x bar mu of h plus mu of h. Therefore, the MMSE estimate is h hat equals sigma h square x bar transpose divided by sigma h square into norm x bar square plus sigma square times y bar minus x bar into mu h plus mu h. This is the simplified. Now, we are going to simplify it further. Okay. Now, we are going to simplify it further. Now, you look at this, I can write this in the form of sigma, I can expand this y bar minus x bar mu h multiplying by the terms, I can write this as sigma h square x bar transpose y bar divided by sigma h square norm x bar square plus sigma square minus sigma h square. Look at this x bar transpose x bar, that is basically your norm x bar square divided by sigma h square norm x bar square plus sigma square plus mu h. Now, look at this, you have minus sigma h square norm x bar square divided by sigma h square norm x bar plus mu h. Now, I can write this as, simplify this as sigma h square x bar transpose y bar divided by sigma h square norm x bar square plus sigma square minus, look at this, sigma h square norm x bar square norm x bar square minus mu h minus you will have well, what do you have? You have sigma h square, of course, there is also norm x bar square into mu h over here. So, sigma h square norm minus sigma h square norm x bar square mu h into mu h, and when you take this mu h, that will give you minus sigma h square. Let me just write this as a separate term. So, let me just write this as let me just simplify this as plus mu h, let me just write it explicitly, mu h minus sigma h square norm x bar square plus sigma square, numerator you have sigma x square norm x bar square into mu h, and now you can see what happens when we simplify this. When we simplify this, what we have is basically we have sigma h square x bar transpose y bar divided by sigma h square norm x bar square plus sigma square plus divided by sigma h square norm x bar square plus sigma square mu h into sigma h square norm x bar square plus mu h into sigma square minus mu h into sigma h square norm x bar square. Of course, these two terms will cancel and what you have is basically net. Now, once you simplify, bring them onto a common denominator, what you will have is sigma h square into norm x bar square plus sigma square into sigma h square into x bar transpose y bar plus mu h into sigma square. Okay. So, this is the simplified expression that you have, sigma h square x bar transpose y bar plus mu h into sigma square divided by sigma h square into norm x bar square plus sigma square. Okay. Remember, sigma h square is the prior variance of the parameter h, sigma square is the prior variance of the noise, the zero mean additive white Gaussian noise V. Okay. And now, what we are going to do is divide numerator and denominator by sigma h square sigma sigma square. So, what we are going to do, divide both numerator and denominator. Divide denominator numerator by sigma square, by the product sigma square sigma h square, and therefore, what we will have is h hat, that is the MMSE estimate h hat. This is equal to, you will get, what you will get is basically x bar transpose y bar divided by sigma square plus mu h divided by sigma h square divided by 1 divided by sigma h square. So, basically you will get 1 divided by norm x bar square divided by sigma square, that is the first term, norm x bar square divided by plus 1 divided by sigma h square, and I can simplify this further just by the last step. I can write this as your h hat equals x bar transpose y bar divided by norm x bar square divided by sigma square by norm x bar square plus mu h by sigma h square divided by 1 by sigma square by norm x bar square plus 1 divided by sigma h square. What we are saying is, this is the final expression, simplified expression, and I am going to explain what is the intuitive meaning behind this. Similar to what we have seen in the case of the wireless sensor network, what we have is a very beautiful interpretation for this expression. Now, if you look at these, the various quantities. So, let us look at this. What is this? This is the simplified expression for the MMSE estimate of the channel coefficient H. So, this is the simplified expression for MMSE estimate of channel coefficient H. Simplified expression for the MMSE estimate of the channel coefficient H. And now, if you can look at this, look at all the quantities that are involved. We have x bar transpose y bar divided by norm x bar square, which is basically the same as x bar transpose y bar divided by x bar transpose x bar, and you can see that this is the maximum likelihood estimate of the channel coefficient H, alright. Some of you might not be familiar with this concept of maximum likelihood estimation if you have not done the previous course, but anyway it does not matter. This is the same estimate that is derived from the based on the principle of maximum likelihood estimation of the channel coefficient H. Okay, so this is the ML or maximum likelihood or ML estimate maximum likelihood or ML estimate of the channel coefficient H. Okay. And what is this other quantity? Remember, there is other quantity sigma square divided by norm x bar square. Okay. So, this quantity we are saying is the ML estimate, this is the MLE, not this quantity is the MLE, maximum likelihood estimate. This quantity sigma square divided by norm x bar square, this is the variance of the MLE. This quantity is this quantity equals variance of maximum likelihood. This quantity is the variance of the maximum likelihood estimate. And now what is mu h? Mu h is prior mean and sigma h square is prior variance. Okay. And this is also what we know, this is the mean. Remember we said h, the parameter, unknown parameter h is random Gaussian in nature, it is random in nature, it is distributed as, it has a Gaussian distribution, prior density is Gaussian, it has mean mu h and variance sigma h square. So, mu h equal to the prior mean and sigma h square equal to the prior variance. Therefore, we also have another very beautiful interpretation of the maximum of the MMSE estimate, that is the ML estimate, maximum likelihood estimate by the variance of the maximum likelihood estimate plus prior mean divided by prior variance divided by 1 by variance of MLE plus 1 by prior variance. So, what is this? This says that the MMSE estimate, this is the so, what does this say? The MMSE estimate is basically a linear combination of the maximum likelihood estimate and the prior mean, that is mu h, in the inverse ratio of their variances. So, this is a beautiful interpretation, and you can see there are several interesting implications of this. For instance, let us look at this. Let us say the variance of the MLE, variance of maximum likelihood estimate, is very small. Okay, it means it tends to 0. Implies, you can look at this, if variance of MLE is very small, then 1 by variance of MLE, correct, 1 by variance of MLE this quantity tends to infinity. Therefore, you can see this MLE by variance of MLE, this is the dominant quantity in the numerator and 1 by variance of MLE is the dominant quantity in the denominator, alright. So, therefore, H hat tends to this quantity MLE divided by variance of MLE divided by 1 by variance of MLE. So, in fact, H hat tends to, in this scenario, H hat tends to simply the MLE divided by the variance of MLE divided by 1 by variance of the ML estimate, which is equal to the ML estimate, and that is a very beautiful interpretation. What we have is when the variance of the maximum likelihood estimate is very small, that is tending to 0, or in other words it is very small in comparison to the variance of the prior. That is basically what we are saying is sigma square divided by norm x bar square is very small in comparison to sigma square. Okay, this is the condition. Variance of MLE tends to 0 implies basically your sigma square divided by norm x bar square is much smaller than the variance of the prior. Okay. On the other hand, if you can see if sigma h square, the variance of the prior is much smaller than the variance sigma square divided by norm x bar square, then what happens? In this case sigma square divided by norm x bar square is the variance of the maximum likelihood estimate. Now, in this case you can see something equally interesting. In this case the opposite happens. In this case 1 over prior mean over prior variance, okay, 1 over prior variance is very small. So, prior mean over prior variance is very large in comparison to MLE divided by the variance of MLE. So, this quantity becomes dominant, in the denominator 1 over the prior variance becomes dominant. So, therefore, what we have, this implies h hat tends to in fact prior mean divided by prior variance divided by 1 over equals prior, in fact it tends to prior variance. So, if sigma h square, if this quantity basically tends to 0 or the prior variance is very small. So, we have two interesting scenarios. What means what we have is the prior variance is very small. If prior variance is very small, then sigma h square is very small, correct, which means that the prior mean, which means that the parameter h has a very small variance around the prior mean, that is mu h. So, to a high degree of accuracy the parameter h is very close to the prior mean mu h, that is what sigma h square close to 0 means. Therefore, the optimal MMSE estimate is in fact the prior mean itself. On the other hand, when you have sigma h square or when you have sigma square divided by norm x bar square is very close to 0, that is the variance of the maximum likelihood estimate is very small. That means that basically with a very high degree of probability or with a very high degree of accuracy, the parameter h lies very close to its ML estimate, that is x bar transpose y bar divided by norm x bar square. So, in this case it converges to the maximum likelihood estimate x bar transpose y bar divided by norm x bar square. Okay. So, that is the implication, that is the practical implication and the insight, the meaningful insight that you obtain from this. So, what you have is basically MMSE is a weighted linear combination of the ML estimate and the prior mean, and the weights are basically inverse, the weights are given by the inverse of their variance, which means the variance is large, the weight is small. So, naturally that is very intuitive, because if the variance is large, that means there is a lot of inaccuracy, hence the corresponding weight has to be very small, and that is the real reason behind combining these two in the inverse ratio of their variances, alright. So, that is the important thing. And now another small point, what do we do when the quantity x bar, y bar and h are complex quantities, when x bar comma y bar are complex? What do we do in this scenario? Then the MMSE estimate h hat is also going to be complex, h hat is going to be, all we have to do is replace by the transpose by the Hermitian. So, we are going to have the MMSE estimate is x bar Hermitian y bar divided by norm x bar square. So, nothing changes except the transpose is replaced by the Hermitian plus mu h divided by sigma h square, and of course, the denominator remains the same, 1 by sigma square divided by norm x bar square 1 by sigma h square. Okay. So, that is the expression for the MMSE, and this estimate is going to be complex. This estimate is going to be this estimate is going to be a complex quantity, H hat is going to be a complex quantity. Okay. So, that is how what happens when the for the MMSE. There is a linear weighted combination of MML, ML and MMSE estimate in the inverse ratio of variances. So, let me also write that down, linear combination of, so this is a linear combination of ML and MMSE combination of MLE comma prior mean in inverse ratio of their variances. Okay. So, this is an important principle to keep in mind. So, linear combination of the ML estimate, maximum likelihood estimate and the prior mean in the inverse ratio of their variances. Okay. So, that is the important point. Let us do a brief example, let us do a small example to understand this better. Let us just do a small example. Okay. So, let me just do a small example for this channel estimation considering complex symbols. Okay. Consider x bar pilot vector equals 1 plus j, 1 minus j, 2 minus j, 1 plus 2j, y bar equals, what is our y bar? Y bar is equal to 3 plus 5j, 3 plus 5j minus 5 minus 3j, 2 plus 3j minus 3 minus 2j. What is x bar? X bar is our pilot vector. And you can clearly see there are pilot vector is 4 cross 1 implies there are n equal to 4 pilot symbols. There are n equal to 4 pilot symbols. Okay. Now, y bar, this corresponds to the received symbols, this is the vector of received symbols. This corresponds to the vector of received symbols. Therefore, we have the channel coefficient H is proportional to the complex normal. Let us say channel coefficient H is distributed as a prior density is complex normal with mean 1 plus j, variance 1. Okay. So, what we have is this is 1 plus j, this is mu h, sigma h square equals 1, mu h equals 1 plus j, this is the, what is this? This is the prior distribution. Since we are considering a complex scenario, the channel coefficient x is complex, its prior mean is complex, that is 1 plus j, and the variance sigma h square is equal to 1. Okay, we are considering a complex channel coefficient estimation scenario. And we have already seen what is the expression. The expression is, so let the noise power, we need some other parameters, let the noise power sigma square be equal to 3 dB, that implies n log 10 sigma square equals 3 implies sigma square equal to, this implies sigma square equal to 10 power 0.3 approximately equal to 2. The noise power sigma square is approximately equal to 2. Next, we want to find what is this quantity x bar Hermitian y bar, x bar Hermitian y bar. Remember, for Hermitian of a matrix, you have to take the transpose of a matrix and the complex conjugate of every element. So, column vector x bar becomes row vector and you have to take the complex conjugate of every element. Okay. So, that becomes 1 minus j 1 plus j, 2 plus j, 1 minus 2 j into 3 plus 5 j minus 5 minus 3 j, 2 plus 3 j minus 3 minus 3 minus 2 j, and what is this going to be? This is going to be, you can calculate this is going to be 6 j. Okay. And other quantity VD is norm x bar square equals magnitude 1 plus j square, this is magnitude 1 plus j square plus magnitude 1 minus j square plus magnitude 2 minus j whole square plus magnitude 1 plus 2 j whole square, which is equal to 2 plus 2 plus 5 plus 5, which is equal to 14, and therefore, our MMSE estimate h hat equals, let us write this expression again once, x bar Hermitian y bar divided by norm x bar square divided by sigma square by norm x bar square plus the prior mean mu h divided by sigma square divided by 1 by sigma square divided by norm x bar square plus 1 divided by sigma h square, which is equal to, now substitute the various quantities that we have calculated above, this is equal to 6 j divided by 14 divided by 2 divided by 14, sigma square is 2, norm x bar square is 14 plus mu h is, remember, 1 plus j divided by sigma h square, which is 1 by sigma square divided by norm x bar square, that is 14 plus 1 divided by 1, that is sigma h square, and this is equal to 3 j plus 1 plus j divided by 8 equals 1 plus 4 j divided by 8. What is this? This is the MMSE estimate of the channel coefficient h. This is the MMSE estimate of the channel coefficient h. Okay. So, you considered a simple example and derived the MMSE estimate of the channel coefficient h. Okay. So, we have done, in just to summarize, in this module what we have done is we have simplified the expression of the MMSE estimate of the channel coefficient h for a wireless communication scenario derived previously. We have given an intuitive interpretation, a nice intuitive interpretation for this expression of the MMSE estimate of the channel coefficient h, and finally, we have demonstrated how to compute this MMSE estimate using through a simple example. Okay. All right. So, we will close this module here and we will look at other aspects in the subsequent modules. Thank you very much.